Mass spectrometry. This is a really important general tool, not just used by chemists, but increasingly used by biochemists and biologists in more of a big proteomics way. But we're going to start with small molecules here to talk about the basis of mass spectrometry. In general, mass spectrometry is looking for the mass to charge ratio of some molecular ion. And the kind of mass spectrometry we're going to start with will only give us mono-ionic things, so things with one charge. So the mass to charge ratio will just be the mass divided by 1, so the mass. So we'll get masses of compounds, which is a huge piece of information for the synthetic chemist. We'll also get fragmentation patterns, even more. So we can't get all of the structural information that NMR gives us, but we can kind of understand how these molecules will break up to give us stable cations, because we kind of understand something about stability of cations now. Finally, and this is kind of a subset of that, but we'll actually be able to see different isotopes of different atoms. And because atoms have different isotopic patterns, sometimes it's a really useful and helpful hint as to what elements we're looking at. Every mass spectrometer has 2 parts, ionization and detection, and how these methods differ in how they ionize stuff and how they detect stuff. Okay? So we're going to start by talking about gas chromatography mass spectrometry, GCMS, one of the most common ways to learn about small molecule structure. We have one at Lawrence. We use it a lot. We didn't use it this term because A, COVID, and B, it is broken. So it's something fun for me to fix maybe my next term. Okay, so our GC oven is simply the same kind of chromatography that you learned about with TLC, right? We're changing things on the basis of their polarity, essentially. But here, this is a separation method. We put a mixture of things in, we heat it up so it gets in the gas phase, it runs through a 30-meter column, and comes out sort of separated by component, okay? When it comes out of this, it goes under a pretty hard vacuum, and then it gets hit with this electron gun. Pew pew. What does that electron gun do? The electron gun is going to knock out an electron from our molecule. So we go from this molecule M to this radical cation. Again, so it's a radical because it has a lone electron. I didn't lose 2 electrons, I only lost 1. So this is an odd electron species, and it's charged. Now, a lot of times these things are not very stable. And so some of them may survive a few milliseconds, but a lot of them are going to break up right away. They're going to break into smaller cations. They're going to break into just radicals. They're going to break into some, maybe spit out some neutral things, and maybe even some smaller radical cations. But here's the trick. I'm going to put a big magnet right here. Right? What's that magnet going to do? That magnet's going to let me pull on charged compounds, but not neutral compounds. Right? And so here, this is flying this path and it feels this magnet, and now that's going to kind of dip like that, right? If you ever held your, combed your hair and then held the comb up to the stream of water and it bends the water because of static electricity, right? It's cool. Science is cool, right? This little cation, right? So it is, let's say it's smaller than the big one. So it's going to be deflected even more, right? Because the smaller it is, the less momentum it has, so the easier it is to divert. But all these things that without a positive charge, so the neutral compound, even the radical, right? The radical doesn't have a charge. They are going to just kind of keep going straight. Now imagine my dotted line is like a special tunnel that I set up, where only something that makes it through that tunnel is going to get to my detector way over here. Right? Everything that's too light is going to kind of be affected too much by the magnet running around. Everything that is not charged is going to hit the side of the tube right away. And so this, again, if I can control the path of the ion, then I can really determine its mass, right? So I can build this tube so that, okay, only this mass should make it to the end of that tube. And then I can see if that mass gets there or not. Okay, here is a slightly better drawing of what I was just talking about. On the left, we see the ionization method. The electron beams are creating ions. I didn't talk about this, but there's a big voltage drop here. That voltage drop is essentially grabbing these ions and accelerating them in this direction. Again, that's not really going to affect the neutral compounds, only the ions. So once we have this nice stream of ions, we're going to set up this magnet, often called a quadrupole. So the magnet is going to essentially make sure that only the particular mass to charge ratio we want can make the turn, right? Stuff that's too heavy, you're not going to bend enough, and so you're going to hit the top of the magnet. Things that are too light are going to hit the bottom of the magnet, okay? So only the stuff that we want, one particular mass, can make it through the obstacle course, right? And then at the end, it's going to hit this detector, and we're going to see a spike, okay? So does this mean that we can only look for one mass at a time? Well, technically, yes, it does. But we can cycle through the mass we're looking for really, really fast, like many times a second. And so essentially, we can look at a really, really wide range of masses like this. And so does that mean we can only look at one mass at a time? Yes, it does. But we can cycle through what mass we're looking for really, really, really quickly, right? Many, many times a second. And so essentially we can look at a pretty wide range of masses with this technique, constantly cycling back and forth and seeing which ions have the perfect mass to charge ratio to make it through the obstacle course. Let's talk about isotopes. So different atoms occur in different amounts of isotopes, and we can sometimes use that information to interpret our mass spectrum. So for instance, carbon is usually carbon-12, but 1.1% of carbon is C13. So that means that for every carbon I have in a molecule, there's a 1.1% chance it's C13. And so if I have, let's say, 10 carbons in a molecule, then 10 times 1.1, there's actually an 11% chance that any given molecule weighs one more than the others because it has a C13 instead of a C12. And so when I see sort of two peaks like that, that's why, right? That little peak that always seems to be above the bigger peaks, those are C13 peaks because, again, some n+1 are that. Nitrogen has a smaller n+1 effect, almost a little bit over a third as big, a little bit of sulfur as well. Oxygen has a very, very small amount of n+2 stuff. So you might see like a little blip 2 in front if you have lots of oxygens in the molecule. Sulfur has a little bit bigger n+2 bump, but the really, really useful ones are chlorine and bromine. Chlorine and bromine have massive n+2 peaks that stick out like a sore thumb. They're really easy to identify. So a peak with chlorine is essentially a 3-to-1 mixture of chlorine 35 and chlorine 37. So if you go to the periodic table is 35 and a half, right? It's not because it has half a proton. It's because 3/4 of it is 35 and 1/4 is 37. So what does that look like? Well, it looks like here's m +2, peak 1/3 the size. Little peak for C13 maybe. Right? So when I see that kind of 3-to-1 ratio, that's a pretty good sense that I should start thinking about chlorine. Bromine is even more easy to spot because now it's pretty much 50-50, literally. Right? So now I'm looking for a pair of peaks that happen to be 2 away. Right? Bromine peaks will look like that. Again, is there something that I can lose that weighs 2? No, nothing in chemistry weighs 2. No atom weighs 2, right? And I can't lose 2 hydrogens at once like that. And so when I see peaks 2 apart like this that are the same height, that is a dead giveaway that I've got 1 bromine in the molecule. If I have 2 bromines in the molecule, now I get to these kind of triplet-y things that almost look NMR-ish.